So uh, synthetic aperture radar essentially is a method of data collection, um, which allows us to get pictures of the ocean with unprecedented coverage as well as frequency. And so essentially, we can get global coverage of the world's oceans every 6 days with a 4 meter resolution, which basically means that each pixel represents a 4 meter by 4 meter square of the ocean, which is an extremely high resolution image taken from space. And so we have this method of data collection that's producing large amounts of data. We have like 600 terabytes of this image data already. And so from this, we can create large data sets for like data analysis and extracting properties of our ocean. And so here are some examples of SAR images. Clearly, we can see that they're very high resolution, so we can literally see oceanography phenomena. So from the top left, we see sea ice. We can even identify boats in the ocean by their wake. We can see that in the top right image. We also see like rain, biological slicks, etc. There are many other oceanography phenomena that we can see from these synthetic aperture radar images. And so our particular problem statement is that we want to be able to predict significant wave height from SAR images. And so significant wave height is an important metric that oceanographers use for their research, and particularly of tracking maybe wave behavior. And so we wanted to be able to predict these wave heights from SAR images because the measurements of significant wave height are a little bit harder to come by in terms of frequency. And so what a significant wave height is it's an average height of the highest 1/3 of all waves that are measured. And so we can use this to not only benefit oceanography research as a whole, but also outside of academia, we can use this for warning ships of extreme sea state conditions because we're able to, with the frequency of these images being taken, we can get more frequent measurements of these wave heights. And so in terms of the current state of the art, current state of the art is based on the concept of these sea wave parameters. And what these sea wave parameters are these 20 hand-engineered features developed by physicists and oceanographers. And they essentially represent a basis for the image modulation spectra. So they basically represent like a reduced dimension representation of the image modulation spectra. And so the very first model was a linear regression on these sea wave parameters. And so this linear regression was trained using buoy data. And so this buoy data produced it's very little data. It's less than 5,000. And they performed a linear regression using these sea wave parameters to predict those wave heights obtained from buoys. And then an improvement on that was a deep learning approach developed by Yannick Glasser in our research group, who developed a deep neural network on these sea wave parameters. But obviously he had to use a different set of data because in order to train deep neural networks, you need large data sets. And so he trained his based on a numerical model called WaveWatch 3, which generates significant wave heights for as labels for his training. And so this obviously also has its limitations as we're training on labels that are generated from another model that doesn't necessarily work as well, especially in extreme sea state conditions. And so we propose the following solution, which requires inference directly from the image modulation spectrum itself. And so we decided to develop a deep convolutional neural network based on the image modulation directly, simply because we're able to construct an extremely large data set using co-locations between the Sentinel-1 missions, which produces the SAR data that we're using, and altimeter space missions, which produces the significant wave heights that we would like. And so I'll go through how that process is done now. So essentially, the altimeter space missions provide significant wave height measurements for regions of the ocean in kind of squares as well. And so we're able to take co-locations between the altimeter and Sentinel-1 satellites to create extremely large data sets. And by co-location, I mean, since the altimeter data points and Sentinel-1 data points each have an associated, I guess, time and space component to them, we can find two measurements that have similar space measurements and time measurements. And so essentially we just set an upper bound and then pick measurements that are close enough to be considered co-location. And so this creates a uniquely large data set that we can then use to train deeper complex models, especially like a convolutional neural network. And so we can see the data is visualized to the right here. We can see that we have almost global coverage of the world's oceans. There's obviously less coverage in regions like near the shore, as well as in more extreme sea state conditions like near the bottom. We also have buoy co-locations. This isn't necessarily used for training our models. It's more for testing at the end to see if, I guess, platform has any effect on our performance. We also have a PDF of the data in terms of altimeter data. So we can see that overall the data is centered on data points between 1 and 3 meters. And this is to be expected as those are kind of the more common waves that you see. We also have a PDF of the distance between altimeter and Sentinel-1 measurements. So essentially the spatial distance between the measurements that we use for co-location. And we can see that for the most part, it's centered on smaller distances. So for the most part, spatially, the measurements are close together. We also show a data count of measurements per satellite platform to show that we do have a decent spread across all platforms. So we split the data set into training, validation, and testing subsets based on year. The reason why we do it based on year is so that we can evaluate our model in the context of being able to determine whether or not, I guess, time has an effect on performance or whether or not instrument calibration has some sort of effect. The reason why we have 3 different subsets is because we utilize a portion for training. We also utilize a portion for validation. So this is used for model selection, early stopping, learning rate annealing that I'll go through later. And then the testing subset is purely used for evaluating all of the models at the end so that we can compare them. So the resulting split is roughly 303,000 training samples, 265,000 validation samples, and 185,000 test samples. So now I'll go over a little bit more about how the data is processed before feeding them into our model. So we take the level 1 SAR image data, and then we apply a 2D Fourier transform to obtain real and imaginary modulation spectra of the image. And so this is then, we then apply standard scaling to the real and imaginary parts separately, and then we stack the two. So each of these modulation spectra had a shape 72 by 60, and we kind of stack them on the third axis. And so the reason why we apply the standard scaling is just for numerical stability. We also use additional features in our model. And these include the time and distance between satellite co-location measurement and so between the Sentinel-1 and the altimeter data points. And obviously when we're predicting new data points, we would set these both to 0 because we would like the real time and the measurement of this particular location. And so we also include time of day, which is scaled between -1 and 1 using the following function. We include latitude and longitude, each of which we apply a sine and cosine to them. So these two features become 4 features total. And then we also include all of the C-wave parameters that were used in the linear regression and the neural network model that I described previously. And so you might be wondering why we include these C-wave parameters when the point was to infer wave height from the image modulation spectra directly. And this is because we're dealing with such a complex learning problem, we want to be able to bias the model to using this information, even though theoretically this information should be contained in the image since the parameters are derived from the image itself. Um, so that was the data that we used. Now this is the model structure, at least. The final model structure obviously contains both a convolutional branch and a regular artificial neural network. So the top convolutional branch is essentially modeled like a computer vision problem where we're trying to reduce the original real and imaginary 2D Fourier transform to a set of features, in our case, 256 features. And then we have the bottom portion, which processes the other data that I described, so the time of day, latitude, longitude, etc. And so this portion of the model is just 11 dense layers and is modeled based on the previous work done in our group, which developed the neural network based on the C-wave parameters. So this also produces its own set of 256 latent features. And then we combine these into 2 more dense layers just to obtain any nonlinear relationship between the 2 different sets of features before predicting our output. And so in between each of these layers, there's a rectified linear unit activation. So for both training stability, but also because we want to make sure that our output is positive. So in terms of model selection and training, we trained hundreds of neural networks using the Sherpa black box optimization framework. So this includes coming up with our final model architecture, but also for tuning hyperparameter, the hyperparameters that we use. So this includes the batch size, learning rate, and dropout. And so the search space is depicted here. But in addition to that, specifically for our model training, we utilize techniques such as early stopping and learning rate annealing. So our learning rate annealing process was basically, we start out the learning rate at 0.00003. And then after observing 4 epochs in which our validation error does not improve, we then reduce our learning rate by 20%. And so what this does is that it allows us to start our learning rate at a higher value, which allows us to bypass a lot of local optimum. And then as soon as we settle a little bit into a specific optimum, by annealing the learning rate, we were able to settle even further down into that minimum. And so this allows for better performance in the end. And then we also use early stopping, which essentially is after 10 epochs of our validation error not improving, we stop the training of our model. And so this allows us to train the best model that we can without overfitting to the data. And so at the end of training, it reverts back to the best validation set performance. And so that's how we did our model training and selection. And so now I'll move a little bit more into the results of what we found. So here we can see that the deep neural network based on image modulation spectra is able to improve performance immensely when compared to the other 2 models. So we did train a linear model and a neural network model based on the C-wave parameters identically to that of the work previously done, so identical to that of the current state of the art, but on our new larger data set. And so we can see that just moving from linear models to a neural network model, we can see that there's already an immense improvement. But then we can also see that in incorporating the image data, we are able to improve even further. And so this shows that the C wave parameters lose a lot of information. In particular, when we reduce from the image modulation spectra to the 20 hand-engineered features, we see that the model loses a lot of information and isn't able to perform as well given the same data set. You might observe that for data points in which the wave height is greater than 8 meters, the performance drastically decreases. And this is common amongst all three models. And this is simply because we don't have enough data that with regards to this category because they occur so infrequently. But even so, we see that our neural network based on image modulation spectra is able to reduce our error in this category significantly when compared to both of the current state of the arts. And this is important because if we were to use this model for warning ships of extreme sea states, it's important to be able to accurately or more accurately predict these. We can see here that we visualized our test performance on the map, so based on longitude and latitude. And roughly we see what we would expect. Essentially, where we have the most co-locations, our average test set prediction is lower. Error is lower. And then we can see that in co-locations that are more infrequent, like near the shores or near the bottom of the map, we see that our performance drops, and this is to be expected because with less data points, our model is less able to learn how to predict these types of wave heights. And so we also perform a platform comparison. So essentially, we compare our performance based on the incidence angle, so the angle at which we collect data. And we can see that there's not much of a difference, which is promising because it shows that, that our model can be generalized to different types of incidence angles. And then we can also see that in varying the platform, we see that the platform sensitivity there's not much platform sensitivity, which is also promising because it shows that our model can generalize to multiple platforms and that specific calibration doesn't actually have much of an effect. We then go through a feature importance study. And so essentially what we did was once we settled on a final structure for our model, we decided to assess the importance of each of the additional features that we included outside of the image modulation spectra. So starting from the right, we see the performance of when everything is included. Then we also look at when we remove incidence angle or mode of data collection and satellite type. And clearly for both of these, we don't have much of a change. In fact, it gets slightly better, and that can be attributed to the noise of training such a highly complex problem. But it's exactly as we saw in our previous results, where we saw that the platform and incidence angle did not have much of an effect on our performance. We see that when removing latitude and longitude, we have a slight difference, but this can be partially contributed to noise. But also we can see that there's not much of a difference. So we can see that our model is able to extract whatever information is provided by location, geographical data, to be able to extract that from the image itself. If you look at when we remove the C wave parameters, we see that there's a more noticeable effect due to the removal. And again, we hypothesize that this is probably due to the fact that we don't have enough data. And so by including the C wave parameters that are essentially information that's already included in the image, we kind of bias our model towards extracting that particular information, which can be useful to predicting significant wave heights. And so we wanted to look further into that to see that that was actually true. And so we performed a test by limiting the amount of training data that we use. So we start with 50% of the data, and then we incrementally increase them to 100% of the data. For this particular experiment, for each data point, we take the average of 6 trials just to kind of smooth out the noise from training such a complex problem. And we see that when we train a model with just the image spectra, as opposed to everything included, we see that as the fraction of training data increases, we see that the difference between the two starts to converge, and we see that the difference gets smaller. And this is promising for showing that as we collect more and more data from these co-locations, because our data set is continually increasing, we can show that direct inference from the image modulation spectra begins to extract all the information that is also provided by the additional features. So eventually, given enough data, the model should be able to predict purely based on the image modulation spectra itself. So in terms of future and related work with regards to SAR image data, if we recall from the first few slides, we saw that we have such high resolution images. And so from these images, we can extract lots of different properties, not only just the significant wave heights. And so we did look into the classification of oceanography phenomena, in particular of classifying these, because if we're able to automate the process of classifying these oceanography phenomena, it can help oceanographers more efficiently process their data and focus a lot more on tracking patterns and such. And so we did some preliminary work with supervised neural network with 10 classes using hand-labeled data. And the results are promising. We see the recall and precision score is really high. But we see the challenge of limited data because although we have such extremely large data sets in terms of images, it's harder to come across hand-labeled data because they take a lot of time to label them and crop them. And so that's one of the challenges we face. And we can maybe tackle this issue by pursuing unsupervised approaches to extract features of interest without hand labels. Yeah, so that's kind of where we can go with an additional route with the SAR image data that we have. So in summary, we're able to generate extremely large quantities of these high resolution images that can be used for monitoring our oceans. From this, we particularly can extract uniquely large data sets regarding ocean wave properties. In particular for our project, it was significant wave height. And so from this, we demonstrated that we can use deep learning to extract more information from the significant the SAR images than traditional feature engineering approaches. And this is better than the previous approaches that use traditional inverse algorithms to predict wave heights because they're slower and perform poorly in bad weather. And essentially, we've demonstrated that the deep learning approach is better and that we can use this for in the data pipeline for SAR images for associating a wave height with each of the images that we have. And so that's all I have. If there are any questions, let me know.
All right. Well, thank you, Brandon. That was a very nice talk. At this point, I open up questions to the floor. If anybody has any questions, feel free to jump in or go ahead and send a chat.
Peter Sadowski here. So I'm the PI. I worked with Brendan on this project. Well, one thing Brandon forgot to mention is that this is already being included in the data processing pipeline. And so people are actually already using this as a data product.
Okay, cool. Well, then let me jump in. I got a couple questions and feel free to throw one into the chat or jump in if you want to interrupt. So one of the things you mentioned through this is really being able to identify these larger sea states. And obviously, I mean, that's a hard problem for anything to measure because nobody knows what's going on. So one of your first assumptions you made was the distance between your co-location. how much of a function do you think that is in improving that if you decrease that distance? Because a lot of times these larger sea states are really small scale cells. So how much do you think that might improve the algorithm if you played with the co-location distances versus removing data? So you kind of are going two ways. You are increasing the accuracy of your co-location, but you're going to reduce your training data that you have to include in the algorithm.
I'm not exactly sure. I guess.
So, yeah, I can actually answer that. In the beginning of this project, we looked at that, and it didn't seem to make much of a difference. So we're looking at distances up to 300 kilometers, I think. And it didn't seem to make much difference in the initial tests we did. I don't think we tested it on the very final model. But
yeah, it would just be interesting on the larger wave heights. I don't think it's going to be as much of an issue on the kind of your mid-range to smaller wave heights, but on those cells where you have these larger wave heights, I could see potentially. But obviously, you guys would be the ones to test that.
That's a good point.
My second question was on your validation data. So one of the big things I've always seen when developing these neural nets for oceanography is how do you pull out the data? So specifically from a satellite, one image to the next might not change a lot. So when you're pulling out your validation data, are you pulling from sequential time periods? Are you pulling out a single track pass across the globe? Or is it like individual images through time? You're just yanking these images through a singular track where there might be some sort of spatial continuity between images that are surrounding your validation images.
Yeah, so for every intersection of two satellites, there's only one image that gets used, and so there's no correlation between two images. Like they're all pretty spread out.
Okay, cool. Any other questions from